Welcome to lesson 8.6, exponential decay functions. So in 8.5, we looked at exponential growth functions. Now, obviously in 8.6, we're switching to decay. So a quantity is decreasing exponentially if it decreases by the same percent for each unit of time. This is called exponential decay. So exponential growth was increasing the same percent over this units of time. Now we're looking at a decrease. So our equation or our model for exponential decay is y equals c, then in parentheses 1 minus r to the t power. So the only thing that switches from growth to decay is this part in the parentheses. In growth, it's 1 plus r. In decay, it's 1 minus r. So c in this equation is still whatever our initial amount is. R is the decay rate instead of the growth rate. And this is a typo here, should not say 1 plus r, it should say 1 minus r. So 1 minus r is the decay factor. So r itself is the decay rate, 1 minus r is the decay factor. And t again is the time unit, or whatever measurement of time we're dealing with. So example 1 states from 1982 through 1997, the purchasing power of a dollar decreased by about 3.5% per year. Using 1982 as the base for comparison, what was the purchasing power of the dollar in 1997? So first, let's just think about 1982 and coming up with our base equation or model. So again, our setup is y equals c, then in parentheses 1 minus r, and parentheses to the t power. So in this case, what we want to think about is the purchase power of a single dollar. So our initial amount c is just 1 for the $1 value. Then we have r, our decay rate. So if it's decreasing at 3.5% per year, we need to take that percentage and, just like with growth models, convert it to a decimal. So we'll divide it by 100, and that gives us 0.035 for our decay rate. And then in our base model, the amount of time in the year 1982, we're just going to think about that right now as being, well, really, no time's passing. We're just coming up with a real model. What matters is from 1982 to 1997, that is 15 years. So when we get over to the 1997, we know we'll have to put a 15 in for t. So our basic model for 1982, we put a 1 in for c, 1 minus our decay rate of 0.035, and technically we're just thinking about that for the first year, so we're going to leave that as a t. So our final model would just simply be 0.965 to the t, because 1 minus 0.035 is 0.965, and anything times the 1 on the outside is just itself. So then for 1997, we know that's 15 years later, so we'll be putting a 15 in for t. So 0.965 to the 15th is approximately 0.59. So that dollar that used to give us a $1 value now has the purchasing power of only 59 cents. So the value of the dollar decreased from $1 down to 59 cents. Example 2 sorry, scrolled too far. Two parts, A and B. It says you bought a used car for $18,000. So we know $18,000 was the initial amount, or C. Value of the car will be less each year because of depreciation. So we know it's losing value, depreciation meaning value goes down, at the rate of 12% per year. So R is 12%. So writing that as a decimal would be 0.12. So our exponential decay model for part A to represent the situation. So again, we have y equals c, parentheses 1 minus r to the t power. We know $18,000 goes in for c, and we knew the 12%, so as a decimal, 1 minus 0.12, all to the t power. So what we need to do is simplify the 1 minus 0.12, which is 0.88. So our model would be y equals 18,000, then 0.88 to the t power. So then in part B, estimate the value of the car in 8 years. So we're going to replace t with an 8. So what we want to do in the calculator is take 0.88 to the 8th power and multiply that by 18,000. That gives us approximately 6,473. So after 8 years, that car that started being worth 18,000 is now down to $6,473. Cars are not a great investment unless you get real lucky with rare models. Example 3 says verify the model that we found in example 2. Find the value of the car for each year by multiplying the value in a previous year by the decay factor. So if we think about our decay factor is 1 minus r. So the decay factor here would be 0.88. So in year 0, the first year, it's still worth 18,000. Then take what it says here, the previous year multiplied by the decay factor. So 18,000 times 0.88 says after 1 year, that car is worth 15,840. Then we'd take the 15,840 times 0.88 to find the value after 2 years, 13,939. And then take that 13,939 times 0.88 to get our next one. Take that times 0.88 to get the next one, and so on. And by doing that, we see the pattern develop. So by the 8th year, that car is down to $6,473. So this table is just a model of this equation right here. Now in example 4, it wants us to graph the exponential decay model from example 2. So again, here was our model. Y equals 18,000 multiplied by 0.88 t. So I don't need to redo my points because I had them in the previous example right here. This would be our x value. This would be our y value. So our first point would be over 0, up 18,000. Next point would be over 1, up 15,840. Over 2, up 13,939, and so on. So when we're creating our graph, we'll notice any decay models should be coming down in a curve left to right. So our value in dollars, I did along the left, and I just went by 2000s on that y-axis. The number of years for the x-axis, and just skipped every other line. So went by 1 year. So now what we want to do is take those points and plot them on the graph. So you would just do each point, and then once you've plotted all the points, do your best to connect them with a curve. And then in part B, it says use the graph to estimate the value of the car in 10 years. So if we'd extend our graph a little bit to see 10 years, That would be roughly in between the 4,000 and the 6,000. So we'll approximate that to be about $5,000. And now example 5. And this one will be important for the upcoming practice sheet as well. We're going to look at two different models. The first thing they want us to be able to do is tell if it's growth or decay. So we're just going to look at how to tell if it's growth or decay. So what you want to do is look at the number inside the parentheses to the t power. If the value inside our parentheses is greater than 1, we have growth. If it's less than 1, such as 3/5, which is 0.6, we would have decay. So if the value in the parentheses is greater than 1, growth, less than 1, decay. So that's how we tell that part. Then it says, in each case, identify the growth or decay factor. So our growth factor is simply 1 plus r, or whatever's in the parentheses. So our growth factor is 1.2. Our decay factor, again, is 1 minus r, so whatever is in this parenthesis here, would be our decay factor. So 3/5 is the decay factor. Then the last part is saying the percent of increase or the percent of decrease for each time period. So this is the part that takes a little bit of mathematical skill to do. I tend to eventually do mine in my head, but I'll show you how to come up with the values. So if we know that the growth rate is just the r part of 1 plus r, we would do, in this case, our growth factor is 1.2. So we'd want to think about 1.2 equals 1 plus r. So to solve for r, we just want the growth rate. We would do the 1.2, our growth factor, minus 1, and that'll give us r. So r in this case is 0.2. But again, they didn't want the rate as a decimal, they wanted it as a percent. So what we have to do is take the decimal 0.2 here, multiply that by 100, or move the decimal 2 spots to the right, and we get 20% for our growth rate. So let's say our growth factor was 2.3. So if our growth factor was 2.3, you would do 2.3 equals 1 plus r. So then we'd subtract the 1 from each side. So r would equal 1.3. And then we would multiply that by 100. And r would be 130%. So if the growth factor is 1 plus r, what we end up doing is taking that growth factor number, subtracting 1, and that gives us the growth rate as a decimal. Then you multiply that by 100 to get the percent. So let's look at our decay problem. So in the decay problem, again, we know it's decay because what's in the parentheses is less than 1. Our decay factor is simply what's in the parentheses, 3/5. And the way that we figure that out is 1 minus r. So in this case, to figure out the decrease rate, it's going to be a similar concept to what we did over here. We would want to take 3/5, so 3/5, which is our decay factor, and set that equal to 1 minus r. So now to solve this, we would have to do 3/5 minus the 1. 3/5 minus 1 is a negative 2 over 5. So negative 2/5. So if a negative 2/5 is what we're left with, that equals currently a negative r. So to get r alone, we would have to divide both sides by the negative. So r would equal 2/5. Now, if that's a fraction, we need to be able to convert it to a percent. So top divided by bottom, 2 divided by 5 is 0.4. And then to convert that to a percent, we multiply by 100. So that gives us our final answer here of 40%. So if we're dealing with decay factors, we could do one more example. And I'll just scroll down here to do that example. So let's say we had y equals, and then doesn't really matter what I put outside of it for an initial amount. So we'll just say 5. But then in parentheses, it was 2 over, let's say 10. And that would be to the t power. So again, we know it's decreasing because 2/10 is less than 1. So what we want to do, if this is our decay factor, to figure out the decay rate, we would do 1 equals, or not 1, sorry, we would do 2/10, whatever our decay factor is. So 2/10 equals 1 minus r. So to figure out what r is, we would do 2/10 minus 1, which is a negative 8. Sorry for the drawings here. Over 10. So a negative 8/10 equals a negative r. So then r would equal a positive 8/10. Then to convert that to a decimal, 8 divided by 10 is 0.8. So we would multiply 0.8 by 100, and we would have 80%. And then let's look at the last part of A and B here in example 5. They want us to graph each model. So in this case, what we would want to think about, if this is my model, y equals 30, 1.2 to the t, I want to pick 5 values to put in here for t. Then whatever answer I get will be my y value. So if I put a 0 in here, anything to the 0 power is 1, so y would just be 30. So this graph is starting over 0, up 30. If we put a 1 in there, 1.2 to the first power times 30 is 36. So we'd go over 1, up 36. Put a 2 in there, we get 43.2. So it'd be over 2, up 43.2. Then we do the same with the 3 and the 4. So our graph, again, along the y-axis here, we would have our y values. So I went by 5s. And across the bottom, we have our x values going by 1s. If it's growth, we should see a curve going up from left to right. If it's a decay like this one, the graphing process is still the same. You pick 5 values to put in here for t. Those are going to be your x values. Whatever answer you get are your y values. So in this case, over 0 up 30, over 1 up 18, over 2 up 10.8, and so on. So because it's a decay, we should see it coming down from the left to right. And again, when you're drawing in your curve, just do the best to connect the points with a continuous curve. So the key to these problems, again, all can be simplified back to this initial exponential decay formula or model right here. What you want to be careful of is, in this case, it's 1 minus r, where in growth functions, it was 1 plus r. And you always want to make sure that you're doing r, the decay rate, as a decimal.